want to follow along on Coffee Casa, I'm going to put in the chat now the instructions to update so that you have the latest version of the notebooks in case you have already cloned these earlier. And with that, please take it away, Lindsey.
Okay, so I'm actually gonna start off with Binder, just so, just because it's quick and it's not using major resources. We'll, for the processor example, it's a bit better if you run it from the open data, or it's a bit faster if you run it from the open data instance, just because there's a better bandwidth and more cores. But yeah, just to dive right on into it, and Nick, please feel free to interject as well. So I'm going to talk to you about kind of how to take this and do a full physics analysis with all the pieces and parts that you've seen, and we'll go through some examples that explain how we've organized the data atop awkward array, and how we use the histograms inside of a scaled out, or use histograms inside of a scaled out analysis and partition the work up and submit it, etc. So of course, the first and most important thing is where do you find this thing? So it's just github.com coffee-team/coffee, and you'll land at this page. And in our case, the what's interesting for us to do is just to scroll down. You can read the description at your leisure, and you want to click the Launch Binder button, and that will land you at a page after a moment like this. And for the purposes of our discussion today, we're only going to be focusing on the Nano Events Python notebook and the processor Python notebook. If you want to understand how we've wrapped up applying corrections to data and things like that, you can click on each of the and histograms and other things. You can click on each of the notebooks as you'd like. There's also small examples of service X and things like that. So, excuse me. Going on to Nano Events. So, is that a good size, and can everyone read what we're going through? And can people give me some thumbs up if they've gotten through loading everything into their browser?
I think maybe one Zoom step more would be good.
One Zoom step more. All right, like that?
Perfect, thank you.
All right, cool. So has at least one other person been able to get Binder up and running and arrive at the same screen, just to make sure we're in sync?
While we wait for people to thumbs up, I'll mention that although this example is kind of CMS specific, we actually now have a Nano Events implementation for Delphi's DAOD Fizzlight and a CMS private end tuple called Tree Maker. And I guess the theory behind this is that in the long run, as we understand better how to form these sorts of nano events objects, that we sort of abstract it so that users can define their own nano events for their own input data, which basically just solves a lot of the bookkeeping issues. You know, you don't have to zip up all the fields into vectors and such, and just does it for you.
Yeah. I think we're finally accumulating enough different views of what trees should look like to really find the patterns, and it's starting to make more sense. Okay, so we've got one other person out there in Binder and with Nano Events up and going. So let's go ahead and start. So what Nano Events is a utility inside of Coffee that takes takes flat n tuples that have, you know, a branch for every single property of every single thing that you'd like to save in the event, and turns that back into a more object-oriented view of your data, like you're kind of one may be kind of used to inside of a T-tree analyzer, where you load one event at a time and analyze the data that way. But in this case, we've organized the data so that it kind of presents this nice object-oriented intuitive interface, but also at the same time gives you access to the data in a columnar fashion. And as Nick was just talking about, this interpretation layer is actually pretty highly configurable. And as you said, we now cover Atlas or Atlas DIOD Fizzlite, Delphi's, etc. And people have been supplying these as they need in order to actually use coffea nano events on top of whatever n-tuples they're interested in processing. And you can, if you want an idea of where it sits in the space, this can be largely thought of as a very rich embellishment upon uproot.lazy, especially due to the fact that it modifies objects and makes cross references and allows you to, explore generator data as well in a very straightforward fashion. So the boilerplate for getting some events expressed through Nano Events is in the first cell. So we're going to do some manipulations later with awkward, and we need to get the thing that builds Nano Events out of root files from coffea. So that's found in coffea.nano events, and we're interested in the Nano Events factory and Nano AOD schema, which is first the thing that will make you the Nano Events object itself, and then secondly, the way that we want to interpret the data file that we're reading. And in this case, it's a little tiny slice of Nano AOD that we use for tests. Okay, so this is an older version of Nano AOD. It's missing a piece, but we're not going to go into those particular branches right now. If you want to see more about what's going on and all the options that are available to kind of customize the object that you're getting, follow the link for the from file method, and you can see all the things that you can do. The event object that you get out of this, and let's just go ahead, insert cell above. If we just events, just go ahead and look at it, is already an object array, an awkward array. That has a particular name, and you can see that it's been formatted to talk about to let you know the run number, the Lumi section, and the event number. And this is the unique identifier of an event within a given data set on CMS. And here you can see from its awkward type that it's 40 times event. And now we'll start digging into each of, in particular, the generator information that's available. So I'm going to go ahead and delete this guy. So in the generator, you can see that there's all sorts of variables available, and you can see the IDs of the IDs of individual particles, mothers and daughters in the event. And you can also see, if you ask for all of the names that are contained within this object, you can ask for dot fields pretty straightforwardly. So this is an easy way to go around and explore the objects that are presented to you inside of events. So for instance, you can I forget if it has fields itself, events. I keep forgetting the S, I'm sorry. Yeah. So if you can even do this starting from the events object itself, and you can see all of the information that's contained within CMS Nano AOD organized into high-level objects. So you'll see familiar things running around here like photons, subjets that belong in jets, gen jets for fat jets, etc. and each of these then have their own fields and behaviors that tend to act like what you would think of as a physics object from an older style analysis framework. Now, if you're just starting to explore your data, you may be confused as to the way that someone annotated a particular or gave the name to a particular piece of the event content. And at least with the CMS Nano AOD, the maintainers have taken quite some care in order to fill in docs descriptions of what each of the branches are. And within Nano Events, we've made it so that those branch descriptions are automatically mapped into doc strings. So within the context of an IPython notebook, you can write out the expression you're interested in seeing and put a question mark at the end. And it will come up, excuse me, it will come up with a description of what this branch is and what all the values are. So in this case, ID1 is the ID of the first parton in the event generator. And you can see that event by event. And you can also get information about the, information about the makeup of the Nano Events object itself, and some basic information about the array as well, in addition to the doc string for it. So you can kind of use this to interactively go after, or interactively understand the parts of the data that you're wanting to use. Yeah, the other thing that we add are a few methods to make things a bit more convenient. So for instance, ginjets are going to have these basic fields, so eta, Fi, PT mass, the parton flavor, and the hadron flavor. But since the ginjets or the generator level jets in this case are also 4 momenta, you can ask for ginjet.energy, and it will calculate that for you on the fly. In the same vein, since you have 4 momenta, you very often want to match it to other 4 momenta in some way. So, and of course, the typical way we do that is by looking in delta R space. So the difference in eta and phi squared, or the square root of the squared difference between eta and phi for each of the partons. And you can do this automatically between collections of candidates and 4 momenta in the event by taking anything that's a 4 vector and asking for the delta R method. So this has been bound up into interpreting the data that was fed in automatically. So you can see here that every time there's a jet and an electron, it's calculating the delta R between the combinations of jets and electrons. And then of course you can take that and ask it to find the minimum delta R between, in this case, the first jet and all the electrons in the event. So here, if you ask for ak.min on an empty array, it'll give you a value of none, but otherwise it's going to give you the minimum value for every single array that exists within this, or that exists within the array that we made with delta R that was matching electrons to jets and calculating the delta R. So now you can combine these 2 statements together and have a very quick matching or very quick construction of a veto criteria. So you can probably tell that there's a lot going on behind the scenes here. And all of the assignment of the methods and the kinds of classes and whatnot is done in the schema object that we passed into the Nano Events factory all the way back up in cell 1. So that knows how to interpret a T-tree layout that it's given. And all of this is actually governed completely inside of awkward array. So you can serialize all of the pieces and parts that we've added as well, using awkward behaviors and manipulating some of the private interface that's inside of awkward array. Yeah, there's a few other things in here. So there, in particular, I think this is mostly a thing of or a peculiarity of CMS. I'm sure other experiments do this too. But we've got a bit-packed set of jet IDs, and instead of just only giving the user that, we've added convenience functions to jets in particular that will unpack this jet ID into the right loose, tight, and medium criteria. So instead of having to do jet ID and then bit shifting and anding to find the right, the tight criteria, you can just do jet ID.isTight. And this makes it much easier for people to get into their data and use, use the objects that we've presented much more quickly than otherwise, because you're kind of containing pieces and parts of the documentation for that object inside the object itself, so it becomes a bit more intuitive to use. So we've also done similar things, at least on the CMS side, for dealing with status flags of GEN particles, for instance. So you can ask if you can get all of the leaves of the particle decay tree in the event by asking for the correct generator status flags. So in this case, we have ones called isPrompt, isLastCopy. So this is telling you that it's a particle that's come from something in the hard scatter and is actually the final stable particle that's presented to JAOT that you're trying, or that you're asking for. So you can see that it's only selecting out some of these, and you can see the fact that the status flag is actually rather packed and has numerous bits being turned off and on depending on the particle that's saved in the generator decay tree. So going into more sort of CMS specific stuff, but I think it serves very well to demonstrate the kind of things that you can encode into high-level physics objects whilst still keeping a very array-based while still keeping an array-based interface that you're processing the event data with. You can also, Nano AOD includes pre-matched indices between like leptons and their generator leptons, or whatever GEN particles underneath, if it happens to be a fake, between electrons and jets, muons and jets, taus and jets, so you can do cross cleaning depending on what you've selected in your analysis. And since we already know those indices, we can alter the electron object to be aware of that as well, and do this automatically for the user so that they don't have to worry about doing the array indirection themselves. So instead of having to do electrons.pt and then getting the matching array or the GEN matching array and passing it into that, and then going and finding the PDG ID array for the GEN particles and indexing it by and indexing that again, we can just do events.electron.matchGen.pdgid and see immediately what all of our electrons are matched to. So either you've got fakes or none, or you've got -11 and 11. So that's working quite nicely. And then similarly, if you're trying to do cross cleaning, the same things are implemented. In this case, there's not that many because it's only 40 events. And then for the GEN particles, we've implemented the same, or we've implemented something very similar in order to get like the PDG IDs or information about the parents and children of the GEN particles. And you can traverse the generator tree for all events with a single call by asking for .parent and .children. So here you can see the initial partons in the event obviously have no parents, and then you can get the then you see that it's coming from quarks, and then you finally get a whole bunch of pi zeros. So and I guess if we asked for just the PDG idea of the gin particles themselves, you see that we got a bunch of photons. So it actually makes sense that we have a whole bunch of pi zeros. So now we can also ask the parents each for their children and ask the PDG ID and see how it maps back onto themselves. And you can see that now we've actually added an extra dimension inside of the awkward array because each of the parents is going to have some number of children. So you need yet another level of nestedness in order to describe the existence of the parent and then what the different child PDG IDs of those parents are. So, and more or less with these two, or this piece of functionality and all of the automatic matching, you can do everything that you're used to doing in terms of generator level manipulation and understanding of the event that you're used to doing with a typical T-tree interface. And Nick, I forget exactly what the distinct parent one does, but in this case, yeah, we're
you know, in particle decay trees, sometimes there's a repeated index for radiation.
It's the last copy.
Yeah.
Okay. Yeah. So in this case, it's the last copy, and we're you know, going into the events, finding the finding the electrons from the hard scatter and asking what they came from. So in this case, that's 23 is a W, right? No. Z, right? Yeah. This is Drelian. Okay. Now we've set up all these nice tools, and this is on top of all of the awkward array functionality. So if you want to do analysis, you start using square brackets, as was demonstrated by Mason earlier, and you start asking for, like, you know, you want the number, you want all the events where the number of events of the number of muons in the event is equal to 2. So you write that down in square brackets notation, and then since all of the muons in these dimuon events that we've selected are 4 vectors, you can actually add them together with the underlying, or with the underlying behaviors that we've added to 4 vectors and candidate objects in this in Nano Events. So you can immediately calculate the Z mass from selecting all of the dimuon events, and then yeah, you can make up variables and add them as you like. So in this case, adding the electron PT for some reason to all of the to the dimuon mass for all the events that we've selected that have 2 muons in them. So you can alter the event as you need. You can make up new variables on the fly, etc., and kind of alter the objects to suit the needs that you have as you progress through your analysis. So we have this nice tool. How do we present it to people? So since coffee version 7, Nano Events has actually been the default way in which data is presented to the user after it's been opened. So if you have, and we'll talk about a bit more about coffee processors in the next piece. And so essentially a coffee processor is a unit of work that executes on a chunk of data. And we'll go a bit more into that later, but this is a very simple one just to show that you can use Nano Events here. So inside of one of these processors, you receive the events that's pointing to some root file or a Parquet file or something. And those events are already a Nano Events object that's interpreting the nano AOD in this case with all of these bells and whistles that I just walked you through. And so you can find all of your dimuon events. You can select that your dimuons have no charge, so that you're getting opposite sign muons and assured to get a Z. So, and then you can finally make your Z to mu candidates, and you can fill a histogram by asking for Z to mu.mass, and then return it to the rest of the event processing chain as a dictionary, pointing to the histogram that we've just filled. So going through this, this one will be pretty quick. And it's not a lot of data. It's only 40 events, but you can still make a plot out of it at the end of the day. There you go. There's your ZP. But due to the fact that we're presenting this immediately inside of the processor, you get all of this functionality that we just walked through for analyzing the event, understanding the generator level data, doing matching, cross-cleaning, etc. It's all presented at your fingertips. And since Nano Events itself is also highly configurable and it can interpret multiple in-tuple formats and so, or T-tree layouts, more or less, you can switch this on the fly to the data that you're trying to process, and very easily go from exploring your data to scaling it out, or to scaling it out on multiple cores locally if you've got like your signal data set local on your laptop or something, and pouring through that. And then you can take the exact same thing with the exact same syntax in the processor all the way to a DAS cluster. And we'll get more into how that's all working in the next notebook. So let's go ahead and take a quick pause for questions. Are there any questions on Slido? I don't have it up, I'm sorry.
Yeah, there's one question on Slido. Can we use custom-made schemas in Coffee?
Yes, so a lot of the contributed schemas. So if we go back to the Coffee repository and we go to Nano Events and we go into schemas, the ones that were made by the developers of Coffee, in particular, this is made by Nick, are Nano AOD and Base. And then every single other one has been contributed by folks in the community. And they originally started off as little projects trying to extend the functionality of Nano AOD. So if you go to the repository and look through the Delphi's, Fizzlight, their tree maker schemas, you can see that they all are inherit from this base schema, which gives you a low level kind of a low level interpretation of the root file. So you get the actual branch names, but it's still organized into this events structure, or this basic event structure that I showed you. And yeah, I would go into one of these Python files where you have a fully implemented example from the community, and try to make one for yourself for your own in-tuple format. The first, like if you're going to embark on this, the first thing you can check to make sure that everything's working okay is just by trying to interpret your T-tree with this base schema, and we'll actually be using that next in the processor demonstration. Because this will more or less read anything that Uproot is able to interpret. And so you can start from the base schema. You can see what your tree looks like once you get it in the base schema, and then start assembling bits and pieces into the objects that you're interested in having in a higher level and more refined schema, like what you get for Delphi's Nano AOD, Fizzlight, and Tree Maker.
Thanks. There's no other question on Slido at the moment, and we have about 20 minutes left before the break. So I'd suggest we continue, and then we can take questions again at the end.
So,
thanks.
Yeah, I think that it's better to spend time on the Nano Events one, because the processor one is actually more just crunching data, and those things take time. And I actually have the notebook cooking show style fully evaluated, and we can go through that to see the answers, because it takes processing the full data set at the end takes a bit on Binder. So just let that run if you want to, but we're not going to do that one in real time. So going back to Binder, we opened processor.ipynotebook. And yeah, so let's go ahead and get on with this. So we saw that coffee mainly relies on uproot to open files. It also can read Nano or any tree or yeah, any columnar format that's in Parquet too. And so our problem then is to figure out how to map an enormous data set onto the work that we, the work that we want to do onto an enormous data set. And we can use that, or in the way that we've implemented that is through this coffee.processor module. And this contains not only a template for building the core unit of an analysis, but it also has it also contains parts to deal with scaling out that analysis and running it in a fairly transparent way. Starting off, the way that you build a processor in Coffee is, and here we're going to do it with histograms and awkward and the standard coffee.processor. Is that you inherit from this processor abstract base class, and of course name it whatever you want. In the constructor, you could pass in configuration data or things to drive variants of the analysis, like what year you're running on, if you want to run all your systematics, stuff like that. And then the real meat of what you're writing is all contained in this process function that you're required to implement, in fact. Otherwise, it will complain at you. And in this case, unless you configure things the right way, the default thing that you get right now is a Nano Events object that expects to be reading a CMS Nano AOD file. And then after that, it largely looks like, it follows the analysis workflow that you're used to. You book your histograms. In this case, we're making a mass histogram that has the or a category axis for the data set, and then a one GeV bins mass axis as well. And right, then once you have the events, you can ask the events for their metadata. So you can ask the events what data set they're in. You can also ask what file is being read right now. You can ask for and you can also ask for any user supplied metadata that you put that you attach with the file set description that you pass in to the thing in Coffee that handles running the jobs, which we'll get to in a second. So here, since we're using, you'll see that we're going to be using the base schema. Instead of having these nice events.muon.pt objects or layout and stuff like that, we've got every single branch in the T tree laid out before us, since we've applied no additional interpretation on top of the events that we're reading in. So in this case, if we want to make a muon object, we got to do it ourselves. And so we want PT eta phi mass and charge, since that's what since that more or less completely defines a muon or for our purposes. And you fill each of these with the appropriate branch coming out of your T tree. So this is sort of the nuts and bolts of how you put together a higher level schema. You can think of it this way. So we're going to have now a muon object that has muons.pt, eta phi mass and charge, and also, since we're giving it this name, it's going to have additional methods for acting like a Lorentz vector with a charge. So you can add it and it will give you values that you expect back in a physically sensible way. So once we have our muons, then we can make cuts on the number of muons, require that the sum is 0 to just get opposite sign dimuons. And then finally, we can do, or we can create the dimuon and plot the mass for a given data set. And then, excuse me, the way that you inform the whole set of jobs that you're running, that you have something something to add together to make a, you know, a histogram summed over all of the files that you're running on, over all the data sets that you submitted. You just return something that you can add or do a merging operation on, like a dictionary. And that applies nestedly to every single piece of data that you return. So we were counting the sum of weights square. We're counting that per data set. And it's going to be some floating point number. And in this case, it's just the number of events that we processed. And then since the number of events that we process can be added together from chunk of work to chunk of work, or the processor infrastructure will actually handle doing all of that summing and merging for us. And then you can sum the number of events, you can merge the dictionary over data sets of the sums of number of events. And then similarly, you can merge this histogram or this the total dictionary that also has a histogram inside of it, which can also be added. So you simply return what you want to sum together to get the final summary of your event and other or any analysis artifacts that you've been making. And you can also define some post-processing steps like scaling your histograms or doing any manipulation or reorganization of data that you'd like. So moving on with that, now that we have a processor to define, or sorry, processor defined, how do we define what to work on? And the first example that we come to is this one, where we're just going to process 10,000 events out of this data set, and we're going to set it to the base schema for Nano Events so that we get everything kind of splayed out in front of us. And you see muon.pt or muon_pt and muon_eta instead of the assembled objects. So let's go ahead and execute that. And you see we're reading, oh, forgot to evaluate the cell, sorry. And you see that we're reading directly from EOS public. So this is the actual open data that's been turned into a Nano AOD equivalent. So we've gotten a histogram out of that. We've gotten our sum of weights, and in this case, it's returning 10,000. So it did in fact see 10,000 events. And everything executed correctly, and we got back the histograms that we were expecting. So that's nice. So how do we take this and within coffea turn it into something that runs over multiple events, or sorry, runs over multiple files and multiple data sets and really starts to scale out? So this file set that, or sorry, this, if you have this file name, you can turn this into a file set that's really more or less a dictionary in Python. And in fact, we usually store it as JSON, so it's easy to pass around and keep track of. And the simplest way to go after this is to just define your data set name as the key in a Python dictionary. And then each data set, of course, has a list of files associated with it. And you add that to the data set, or you add all of the files that belong to that data set under that key. So simple, straightforward to use. And here we've done it for ZZ4mu data set as well. And you just keep building up this dictionary until you've defined all of the data sets that you want to process on. And here we're going to, here we're going to do a quick local run, and I'll actually, I'll go over to the one that's running on the analysis facility since it's already run all the way through. And we're going to pass in the base, so now we're going to set up the infrastructure that deals with generating all of the jobs, mapping the jobs to ranges of events in particular files, and doing all the bookkeeping for you. So the way that you enter into this is by looking, or by creating a processor.runner class. And within this runner class, you have to pass it an executor so it knows on what resources it's going to be running your jobs. And there's a variety of executors that you can use, and for us right now, the one that we're using is the Iterative Executor, and it has a few configuration options, and we're just telling it here to not do any intermediate data compression because this processor is pretty small. We need to tell it again what schema to use. And for those of you following along at home, this max chunks equals 4 is more or less to make sure that this doesn't take an infinite amount of time, because reading from EOS public can take quite a bit. And in fact, this takes around 5 minutes to run, doing everything with the iterative executor, which is single thread execution in the order that the files are listed in your data set, more or less. So it can take quite some time, especially if you're reading from a slow source, just because you're not exploiting parallelism, etc. So I'll leave you guys to run that yourselves, but you'll see that now you get, of course, different numbers out. You see that we've run over the ZZ to 4mu data set, we've run over double muons, and we get, as we expect, we get different numbers out. And we've filled up this histogram over the data sets that we have, for each of the data sets that we have in this string category. And then within each of those, you've got a mass histogram in 1 GeV bins from 60 to 120. Now, obviously, there's better ways to process a data set than just running over each one at a time. So the first way in which you can do this is by switching instead to a futures executor. And what this means is that you're using the Python package concurrent.futures in order to spawn multiple processes that run over your data set in parallel, based on the chunks that based on the chunks of the files that you want to process. So in this case, instead of the iterative executor, we use the futures executor and set that as the executor for our processor.runner. So now we have something that knows it should use multiple cores in order to process whatever you give it. And we've set the number of concurrent workers to be 2 because the VMs that you get in Binder are pretty dinky. Of course, if you're running this on the analysis facility, you can bump this up to 8 or so, and you'll see more parallelism. And you'll find that you get the same answer as you did with the iterative executor. It's just that you'll probably get it in about half the time since you're running in parallel. So this one I'm going to not go ahead and wait for because there's not really too much to discuss. And sorry that the annotations up here are out of line with the interface that's being used. What's being used in the cells is basically a completely rewritten interface that's a bit more extensible for building things that consume and process data within coffea. And we'll update that. We'll update this piece of the documentation later, but the cells are correct in what you should be using. Now, this muon or this dimuon processor that we showed you is pretty simple. I mean, you can get a ZPeak out of it. That's great. But what if you want to do something much more interesting? What if you want to make use of this ZZ to 4mu data set that we're pointing at and ask some more interesting questions of it? So in this case, scrolling down a bit more, so since we're using awkward array, since awkward array can talk to just-in-time compilers like Numba, you can build in fairly complex combinatorics by going to the event or to the old loop-based analysis when you need to, compiling that code and running that in the case that you may need some fancy combinatorics that make sure that you only select certain pairs of Z's and doesn't double count anything.
Sorry to interrupt.
Yeah.
You have about 5 minutes left.
Yeah, I'm just going to run through what this one does, so we should be about done. So you can go and see that we've implemented such a function in this find for leptons. function, and we have annotated it with this @numba.ingit. And what this will do is when we call this function, it will be just-in-time compiled on or in one of the process, or when the processor calls it, and it will take this fairly heavily loopy Python code and turn it into something that executes just as fast as if it were in C++. And not only that, but since awkward does have a numba interface built into it, you can return an awkward array from this using this this builder interface here, and that's literally like another hour talk, so we're not going to go really deep into that. But just take this as an example of how you can get really advanced and detailed functionality into awkward array using Nano Events at scale with the coffee processors. And then finally, you can see that we've built this fancy daimyo processor that uses this function find for lep here. And we've generated or made a bunch of histograms. We fill those histograms, we build our muon objects, isolate them, etc. And then fill up the final histograms that we want to send out for analysis. And finally, just to show you that all of this stuff actually does work at scale, I slightly modified the notebook and the fancy daimyo processor in the one that I was running on Coffee Casa to, instead of using the futures executor like what's in the binder version, it uses Dask. So Dask is a module in Python for running very parallel applications and running them on top of computing clusters as well. So in this case, the executor type that we were using, and let me zoom in on this, I'm sorry about that. The executor type that we're using is this Dask executor, and we're pointing it to a job scheduler inside of Coffee Casa. And then we say that it can retry a job 10 times in case xrootd fails for some reason. And it doesn't have an open data xcache, unfortunately. Nick. So yeah, so we take this Dask executor, we pass it into the same runner infrastructure that we were using before, and pass it the base schema so that all of the data is organized how we expect. And we can actually then immediately run this on Dask at Coffee Casa using the same code that that was in the binder example running locally in parallel on whatever VM got spun up for binder. So with that, you can see that this processor interface allows you to build code that's highly portable, pretty concise because of all the expressive power of Nano Events that's built in, and also easy to, and then therefore easy to scale out because we made it such that all of these different executors are interchangeable. And with that, I think I'll wrap it up and just say I think that's a reasonable overview of how we do analysis with Coffee and all the pieces and parts that are available to you. We've got, or just to put it in context, and Andre and a few other people here are using Coffee at scale as well. We're running this with, at this point, thousands of jobs in real analysis, people using actually very recently people using BDTs and multivariate analysis inside the processor.process function, etc. So this pattern that we've come up with does seem to work, and it's actually fairly mature at this point. So thank you. I see we have one question from Doug. Are there any memory limits with Dask Coffee? So the answer is you configure them. For Coffee Casa, the memory limits are about 4 gigs per core. Sorry, 2 gigs per core, and you get 2 cores per worker. And it will, there's an issue today with the cluster, but normally it will actually automatically scale onto Condor and show it scaling up and down and adapting to your work needs. And if you were doing this in a more manual way, like configuring the options for the job and whatnot, you can set the Condor memory requests from the instantiation of the Dask client. or sorry, the Dask cluster, and like add in memory requests for 4 GB and 2 cores or whatever you need. So it's you can get some pretty fine-grained control. And then to answer the final question in that, if you do go over the memory limits, Dask will kill the job. So it's actually watching them too.
Thanks. We have 2 questions also on Slido.
Yeah, sure.
The first one, does metadata have to be put inside the input file, or can you also pass it from an external file?
Yeah. So inside of this file set that we've made here, it's just a regular Python dictionary. You can change the list here from a list to a dictionary, and then we have to say, okay, so these are files, and they're in a list. And oh, sorry, I'm too used to pressing Shift Enter at this point. So is let's say you just wanted to add is data. So the way that you add metadata is by annotating this file set and adding in the pieces, or adding in the pieces and parts that you want, and then it will show up inside of the let me complete this guy. Files. So if you did something like this and you go up here, you'll see that all the events have this metadata property already added to them. And you could say is data equals events.metadata. And you could do something like this. You can also, and yeah, so long as it's pickleable, you should be able to, or maybe even JSON serializable. I can't remember exactly what the limitation is off the top of my head. You can pass in whatever you want, but of course, be careful about the size of what you pass in. But you can get pretty extensive with the metadata through this part of the interface, just by editing the way in which you, or just by changing the data set definition from a list of files to a dictionary that has the list of files in it, and then putting in all of the extra decoration that you would like for each of your data sets.
Thanks a lot. There's one more question on Slido. How can we implement event kinematic dependent weighting on events in Coffee? For example, applying trigger scale factors based on lepton kinematics.
Oh yeah, so that is actually another binder. So if you go and click on applying corrections, you'll get a pretty decent overview of how you not only build lookup tables for efficiency scale factors and stuff like that in Coffee, or even, you know, kinematic based reweightings from generator quantities and stuff like that. If you have a K factor, just generally some sort of lookup table, it'll show you how to build those up. And then it will also, this notebook will also show you how to apply that as weights in a histogram. And then if you go on to the histograms example, you'll also see how to do this looping over systematics and things like that. So that's completely covered. We just didn't have time to properly get into that today. And since it's all part of the, or since in this case it's all part of the Coffee package, it's immediately available at the workers that you're putting your jobs on, so it scales as well. But yeah, that's something you can. I'll leave this as an exercise to the reader. So go ahead and give it a try and see if it's enough. And then ask more questions if you're further interested.
Thank you very much. I think we then will leave it at that.
Okay.
Thank you very much for this overview of a Coffee. We are now going into a break, and we're going to continue with the workshop on time, which is going to be in 22 minutes, 6:15 Central European time, or in 22 minutes in wherever time zone you're in. Thank you very much for all the speakers, for all the material, for all the participation so far, and talk to you again in a few minutes.
Bye, and thanks.